Hi, welcome to module number 29. We're going to speak about linear regression. And after setting up the problem, describing a real world example and so on, why it's, hopefully you'll be motivated to see why it's useful, we'll go from a multilinear problem, the general case, to a problem where there's a single variable that's we try to estimate. And we'll work through that in detail, and that'll give us some insights how to possibly approach a multivariate problem. And then in later modules, we'll go to more sophisticated techniques. So recall the linear model. Y hat is equal to B hat 0. It could be like a DC coefficient plus a summation over P terms, summing over J from 1 to P of xj multiplied by beta hat J. So the beta hats are basically coefficients. And the linear model is tractable. It often works well. Many things are well approximated by linear. And because of that, it's been studied for centuries. And if you think about it, there's a favorable feedback loop between the math and the algorithms for linear models. And these are increasingly mature. And because they're increasingly mature, people use these math and these algorithms. And moreover, it's not only in the machine learning world. There are hardware designers that they try to design hardware that's approximately linear, because then that hardware, the outputs of the hardware, what it measures, can be processed by these linear styles of math and algorithms. So there's this entire process that, because we know how to do linear processing well, we build more and more systems that are close to linear. Okay, so let's kind of pause and ask ourselves, what's the meaning of x? So again, y hat is a linear combination of xj multiplied by coefficients b hat j's. And the coefficients, recall, this is a model. Because this is a model, the xj's are explanatory variables, and the beta hats are coefficients that might explain how the x's relate to y, all right? But now let's ask, what could those coefficients xj be? So they could be the actual inputs, meaning that, imagine that we have patients and we're trying to predict, will you have a heart attack or not, or how severe will it be, etc. So this may be the actual raw data in X, or it could be functions of the inputs. So instead of, let's say, X being my height, maybe it's a logarithm of my height, or the square root of my height, or other functions. And we're going to revisit this sort of style over the next few modules. Maybe we have polynomials of the input. So we have entire Taylor series approximations that are added in. So imagine that we begin with 10 x's, 10 explanatory variables, and then we add 30 different functions of these 10 explanatory variables, and then we add 50 different polynomials. So there's an entire world of things that can be created from the initial core data in the first category. Now there could also be, imagine that we have classes. We know whether something is red, green, and blue, and what we have here is a numerical model, right? We have, this whole thing is a linear combination of the x's. And because of that, we encode the classes, the red, green, and blue, into numbers, and that allows us to have a coefficient that picks up the class. And finally, there can be, just to make it clear, I mean, earlier I was talking about polynomials of inputs. There can also be interactions between multiple variables. So x3 could be a product of x1, x2, not just monomials, but also polynomials with multiple terms and different raw inputs. Okay, and overall, this function could be nonlinear in the underlying factors, but if we begin with 10, 20 raw inputs and we add in nonlinear functions of them, then this linear model form could actually be nonlinear in the raw underlying data. All right, so now that we kind of understand that this covers a lot of ground, it's not just linear in X, but we can add in more x's that are actually not the raw data, they're functions of the raw data, and now it's a linear form over nonlinear terms. And let's at least put that aside for now and ask ourselves, how can we solve this linear problem? So the classical solution, I've mentioned Gauss a few times during the course. In 1795, he started working on the least squares method, where he tried to minimize the sum of the squares of the errors. As we've chatted before, the error is a function of the beta. The beta is a vector of parameters, and each yn is explained as xn transpose multiplied by beta. Xn itself is a column vector, xn transpose is a row vector, and beta is a column vector. So to try to sketch this, beta column, xn transpose row, row times column equals scalar, and of course, yn is also a scalar. So we're squaring a scalar, and we're summing the squared scalars, and that's the metric for the error with the vector of parameters beta. The closed form solution, we've seen this before for least squares, is that beta hat is the inverse of x transpose x multiplied by x transpose multiplied by y. So this term is called the pseudo-inverse and often expressed as x superscript with a plus sign. Now there's a geometric interpretation here. You can interpret the inputs as a matrix. You have a column of ones that corresponds to a DC coefficient, x1, x2 up to xp. All right, so let me sketch this. X is 1 in my first column. So these are multiple ones. X1 in my next column up to xp. And imagine a vector space spanned by the columns of x, including the 1, all right? So we have this new thing. So we have the 1 is one of the axes, and we have x1, x2, x up to xp are different axes, and we're looking at y. Y is a vector, and we're projecting it to the space in the vector space, to the subspace, the plane, what appears to be the plane in this illustration, spanned by all of these columns. So projecting meaning we go from y to y hat, where y hat is the closest point in the entire space, which is spanned by the columns of x. All right. Now it turns out that y minus y hat is orthogonal to the span space. So this thing is often called y perp, perp for perpendicular. Perpendicular means orthogonal, right? And the y is mapped to y hat, and that explains why y hat is a good explanation. We project it to the nearest vector in the span space. All right, so let's move on. And so that's a possible solution. That's how Gauss would have done it in the late parts of the 18th century. And let's discuss, let's kind of provide a motivating example. My motivating example, I want to tie this into something that could appear in applications because it may be somewhat abstract at this time. So let's think about financial prediction. Yn could be the future percentage change in the prices of stock number lowercase n, where there could be perhaps capital N stocks, right? So let's again annotate. We're going to have y1 up to y capital N is a vector. Each of the elements of that vector corresponds to a future change in the price of a stock, capital N different stocks, and xn1, so this would be yn, xn1 would be the earnings to price for stock number n. Now what is earnings to price? It's the ratio between the earnings, the profit that a company has, and the price that the financial markets are pricing the company. So for example, maybe, I'm just making these numbers up, I have no idea how accurate they are. Maybe Apple's earnings, their profits in a year might be $50 billion, and their price might be $1 trillion, and 50 billion divided by a trillion is 5%. All right, so 5% or 0.05 would be the earnings to price of Apple. Let's say there would be another company. Let's say the company has 0 earnings, okay? So irrespective of the price, the earnings to price is 0. So we have x11, xn1 up to x capital N1. This is the earnings to price column. And then we have xn2, the book to price. So let's write here E divided by P. This could be E2P, 2 with like the numeral P, or E divided by P, different ways how to write this. And the next column will be book to price. And what is book? We understand that price is how the market gives a value to companies. The book is how much accountants value the company's assets and liabilities. So on paper, if, let's say Apple again, suppose that the market values them as $1 trillion, and suppose that they earnings or profit. Suppose that they own $300 billion of assets, and they owe $100 billion of liabilities, debt, okay? So 300 billion minus 100 billion is 200 billion. Their book value would be 200 billion, and the price would be $1 trillion, so the ratio would be 0.2. Now, let's think about these factors so far. For the first one, for earnings to price, for the same price, if you have large earnings, a high earnings to price ratio is favorable, all things being equal. So we expect that if the earnings to price is higher, on average, the stock price will go up relative to other companies where the earnings price may be lower, okay? Now, similarly, the book price, if the book price is higher, then let's say some change in the economy happens, the company runs into some minor challenges, they can increase their debt a bit to overcome the challenges because they have a lot of assets. They have a high book value, all right? So a high book to price ratio is, again, favorable. All else being equal, it's a good thing. Now you can imagine that on average, companies with a slightly better earnings to price and book to price, their stock price would be higher. So on average, the market would already integrate this information. But if by chance, by luck, a company is slightly undervalued, so yeah, it has these ratios are favorable, but not as favorable as you'd like, that might be a buying opportunity. So let's say a third column could be the price change over the last 6 months. Now, why am I mentioning this? You might think, well, the market is perhaps reasonably integrating the current information. Well, it turns out there have been a lot of studies that show that recent price changes, which are called price momentum, tend to keep going. And there are different reasons why this has been, that have been hypothesized to try to explain this. All right, so there can be a lot of variables of X, imagine 50 variables, and that would be the raw data. There could be other variables that are functions of this raw data. And so overall, we're gonna have, an X vector multiplied by a beta vector plus noise, an N vector noise. So what I'm saying is that the returns in our training data are X times beta plus N, again, N noise, and we want to estimate betas that provide a good explanation for the Ys. If we can do this, we might be able to, on the future data, again, this is training data, on test data in the future, we might be able to predict the future returns well and make some profits from them. All right, so let's move to the next slide. Let's continue this example. How can we predict the future returns? We'll form a linear model, some linear combination of beta hats times the x's. We'll compute the parameters for beta. It could use least squares. It could use other approaches. And again, we'll discuss multiple more advanced, more modern approaches for linear regression. And then we apply the parameters from that were learned to predict the future returns. So now, as I said earlier, after providing a motivating example and explaining least squares, I want to move back to a univariate case where we have a single explanatory variable, and then I'll return to the multivariate situation. So here we have y equals x beta plus epsilon. X is going to be a vector of observations. Y is going to be a vector of observations. But when I'm saying vector, there's not a matrix X with multiple columns, there's a single column. That column is multiplied by a scalar beta plus vector noise. Now, we're going to show, and I'm going to do this in a moment, but this is in the supplements. You can go look at the supplements later. We're going to show that the optimal beta is summation over xn yn divided by summation over xn squared. All right, so let's work through this step by step. So error of beta, let's call it B, all right? It'll be easier for me to type. Error of beta is going to be sum of n going from 1 to capital N. Capital N will be the number of elements in the y vector, the x vector, and the epsilon vector. So earlier in the previous slide, I used lowercase n for that vector, but epsilon, n, z, whatever you want. All right, so what are we summing over? We're summing over the errors. So we're summing over xn times b is our possible explanation, our model explanation, but we're subtracting that from yn. That's the error. Yn is the true nth observation. Xn times b is the predicted nth observation, and we're squaring that. All right, so that's error as a function of b for beta, and we want to optimize beta. And I'm just, in red, I'm typing to clarify this is beta. So optimize meaning want to minimize error as a function of b. So we want to find the beta, the b, that minimizes this expression. All right, so let's take the derivative. Derivative with respect to b. All right, so error b, before taking the derivative, let's just simplify it just a bit. I want to remind you that each of these terms is yn squared minus 2 times yn times xn times b plus the square of xn times b. And I'm just putting square brackets around this whole thing. I just want to add a bit more detail of what we're taking the derivative over. So error prime of b, prime for derivative, is again the same summation as before. And now let's think about the derivative of the first term. Well, beta doesn't appear in the first term. Yn squared is independent of beta. The derivative of the second term is, well, we do have a product with beta, so the derivative of minus 2 yn xn beta is minus 2 yn xn. And what about the derivative of the square of xn beta? So that's xn squared beta squared, and the derivative of that is 2 beta times xn squared. All of that, we want it to be 0 for the optimal b. So sum over the lowercase n's. We can break this up into 2 sums. -2 times sum over yn times xn plus 2 times, the beta is the same beta, okay? So 2 times beta times sum over xn squared is equal to 0. Now, the 2's cancel out, and moreover, the first summation can move to the right-hand side. So we have that the summation over yn times xn is equal to b multiplied by the summation over the squared xn's. So overall, the optimal beta is equal to summation over the yn times xn divided by summation over the squares of xn. And this is what we have over here. The optimal beta, beta hat, beta star, however you want to call it, is a summation over x and yn divided by summation over the squares of xn. You can derive this, and I believe this is done in the supplements, that x is going to be a vector of xn's, y is going to be a vector of yn's. The inner product between x and y is going to be a summation from 1 to capital N of x and yn. And now beta hat is an inner product between the x and y vectors divided by an inner product between x and itself. Additionally, we can easily calculate the residual, the error, between y minus x times beta hat. All right, so again, you can look into this in just a bit more detail in the supplements. So that's the univariate situation. What about multivariate? Suppose that the columns are orthogonal. So in the univariate case, we had a single column. Now we have p columns, and if they're orthogonal, then for every 2 columns whose indices are j and k, orthogonal would mean that the inner product between xj and xk is 0. And we can show that if the inner products between every pair of columns is 0, then beta hat I is an inner product between x and y divided by an inner product between xi and itself. The challenge is that real data is not orthogonal. One possible solution is to orthogonalize it. For example, in previous and undergraduate courses, I'm sure you've heard about the Gram-Schmidt procedure. There are ways how to orthogonalize a matrix. However, orthogonalization can be numerically sensitive in addition to other problems. So we went to univariate. This can be used in a multivariate case, but this requires, one needs to proceed with care. So this is going to be the end of module 29, and in upcoming modules, we'll be discussing more topics related to linear regression.